Let's talk about unbalanced forces. So we have this dog and it's pulling on the string of this shoe. What's going to happen to the shoe? It's going to move, right? So we have these force vectors. Let's go ahead and give a name to these. What should we name the force vector to the left here? And why? What's the dog pulling on? A string. What kind of force is that? Tension. Excellent. So we're going to put FT here. And then what do you think is this opposing force? Like what force could be moving this way, keeping the shoe from dragging? The friction force, right? So if we're on a surface, we would have friction force being the opposite direction. So what'll happen is unbalanced forces will occur when they are not equal in size and or direction. Now I say and or direction because maybe you only have one force, right? So for example, if I were to move my pen here, all right, so I'm applying a force. Does everybody agree? And there's friction working against this. And if you're close enough, you can actually hear that friction working against this, okay? But here's the thing. If I just hit it, okay, so I hit it or I click it and I cause it to move, why does it stop? Because of friction. The thing is, if I'm not touching it, I'm not applying a force to this, right? Now, I made it move, but I didn't keep it in motion, okay? So if let's do something a little bit bigger. So if I'm using this and I move this, it comes to a stop because friction is the only force working on it and it opposes the motion. So when we talk about unbalanced forces, when we talk about unbalanced forces, we don't have to have multiple forces. We could just have one force working on an object to make it move or to make it stop. Make sense? Okay. So they're not going to be equal in size and or direction, and what will happen is the net force, so the total sum of the forces, is not going to be equal to 0 newtons. And then maybe we should put here, so it doesn't look like on, let's put newtons here and newtons here. Okay. So what will happen is unbalanced forces, they do cause a change in motion. They do cause a change in motion. So what will happen is the dog's tension force is stronger than the force of friction. Which way will the shoe drag then? In the direction of tension, you bet. So we're going to say to the left. So it's going to be in the direction of the tension force, okay? So let's take a look at the net force equation here, you guys. So here I have net force. Net force, all I'm doing is I'm adding up all the forces working in the same direction. So here I have my horizontal direction, left and right. And if I add these up, I get a negative tension force plus a positive friction force. So this is my net force equation. This would be me just adding the two vectors. Okay? Now, since Ft is larger than friction, which is Ff, the net force is a negative value Okay, so the net force is a negative value. And in this situation, it's going to cause the shoe to move this way. Okay, that does not have to be the case though. So remember, when this was sliding, the paper was sliding, right? The motion was to the right, but the force was, am I saying it? It's the object was moving left, right. It's very hard. The object's moving left, but my force was only right. It was only the friction force to the right. So my net force was to the right, but my motion was to the left. So don't be confused with saying, well, if the net force is in this direction, it has to be going that way, because that's not a true statement. Like, you have to take the whole situation into account. What way was I moving? Which way is the force directed? If you're moving in the same direction as the force, then yes, what will happen is you end up going faster in that direction. If you're moving in the opposite direction of the net force, that means you're going to slow down. Okay, so that's how it's going to change your motion. All right, so let's take a look at the last piece. All right, so the net force is the sum of all the forces working on an object. Okay, so the net force on an object is the combination of all forces acting on the object. Net force determines if and how an object will accelerate. So if you have forces working in opposite directions, and those forces are not equal, then what's going to happen is you're going to have a magnitude. What's magnitude mean again? The size of the vector. So you have a magnitude equal to the difference in newtons between the two forces. So if I came up here, if this were 20 newtons and this were 5 newtons, then I would have a net force of negative 15 newtons. So the size would be 15 because that's the difference of the two vectors. But the direction is going to be the same as which one, which force. So is the large one, good. The biggest one. So whatever the larger force is, that's going to be the direction. Okay? All right, so let's take a look here. We have a boy is pushing a chest with a force of 200 newtons. The girl is pushing with a force of 150 newtons. Draw the force arrows and calculate the net force on the chest. Okay, so we're going to get into more of this tomorrow, but I'll do a little demo. I'm going to put a dot here, and this dot represents this chest. Okay, now, is the girl's force to the right or to the left on the chest? The girl's pushing which way? She's pulling, yep, so she's to the left. And how much is she pulling with? 150 newtons. Okay, and then the boy is doing what? Pushing to the left. So he is 200 newtons. So what is the net force here? It'll be, and it's up to you, we can assign left. Yeah, we can assign left to be positive if we want, or we can assign it to be negative. If I make left negative, this is going to be negative 150 newtons plus negative 200 newtons, which is going to equal what? Negative 350 newtons, which means the net force is really 350 newtons to the left. Okay, so it's going to have direction. Does that make sense? Okay, and let's make up a scenario here. So we have this girl, and she is biking, and so she's applying a force. So we're going to have an applied force this way. So this is going to be FA, which is the applied force. And we're going to say that this is going to be 20 newtons. And then what is this force over here? So this is FA. What would this one have to be? The friction force, you bet. Friction force. So FF is friction. So our friction force, we're going to let that be 15 newtons. All right, and what I'm going to do is I'm going to put 5 here, and I want you guys to tell me, what does that mean? What does this number represent? So in this scenario, what does 5 represent? The difference. And when we find the difference of the forces, what kind of force is that? The sum of the forces. What's another name for the sum of the forces? The what? The net force. Good job. So the net force is 5 newtons. So the net force equals 5 newtons to the right. Okay. Now, just a quick page for references. If you turn to the next page, what we have is a list of common forces. This is not all the forces, but we talked about some of them today. Field forces are forces that work on objects without being in contact. So the one we know the most is our weight force, Fg, right? Because that is pulling regardless of where you're at. If I have an object in the air and I drop it, it is going to be pulled to the closest surface. Okay, we have electric and magnetic forces. Our most popular are the normal forces. How do we have a normal force? What has to happen in this situation? There has to be ground or a surface, a desk, a chair. It has to have an object sitting on something. Friction is opposite the motion. Drag is your air resistance. Applied force is pushing. Spring force will be a spring, and tension is your rope or your string or anything like that.